Hey guys, we're going to be exploring the fundamental theorem of calculus. That's what FTC stands for. And you can use FTC, that abbreviation, in your work as we talk about the fundamental theorem of calculus. Yeah, okay, so we have been finding antiderivatives, indefinite integrals. We've also been finding area in the regions between curves and the x-axis. Now it's time to put all that together. Yeah, so what's the connection between an antiderivative and the area under a derivative graph? So that's what these notes are all about today, is to explore that connection. All right, so we're going to sketch y equals f of x equals x squared, and we're going to label these points. And then you're going to find f prime of x and sketch a graph of that function. So here we have a sketch of y equals x squared. I took the 5 given x values and I plotted them and I labeled the points. So now I'm going to come over here. I'm going to find the derivative. Easy enough. The derivative is just 2x, a linear function. I'm going to sketch that graph. Something like this. Okay, so we have a function, we have its derivative, or if you want to think about it, we have a function and its antiderivative. So let's go down here to what's requested of us. So here in this column, we're asked to find the indicated values, the values from the original function f of x. And we know that we're finding y values from the original f because of the notation. That's f, that's not f prime. So looking up at the graph, f of 2, 4 minus f of 1 is 1. Easy enough. The change between the two y coordinates, where x is 1 and x is 2, if you think about it, right here, the difference of those two y's is 3. So we're just subtracting the y values. Easy enough, I know, but it's when we come over here and we put it all together that you go, oh, I see the connection. All right, what's the change in the two y values when x is 0 and x is 3? Well, 9 minus 0 is 9. So a graphical representation is you're looking for the change vertically between this point and this point right here. So the difference here to here is 9. We see that's very obvious. All right, f of 2 is 4. I'm going to subtract the y value over here at negative 2, which is also 4. So the difference in those two y values is 0. So there's no change from this y value to this y value here. They're equal. All right, and the last difference, all right, f of 1, which is 1, minus f of 2, and f of 2 is 4. So if we think about it, we're taking 1 and subtracting 4. We're taking a small y value and subtracting a larger y value. So that change is negative 3. All right, so we had some positive answers, some negative answers, and a 0 answer. So easy enough, find the difference in the two y values on the original function f. All right, so let's come over here and look at this column and what we're asked to find based on what we've done so far. So based on our work so far, as I study number 1 here, if I'm asked to find the indicated value, I think about f prime of x, and that's this graph right here, 2x. I think about y equals 2x. I think about f prime of x equals 2x. I'm asked to find the value of the integral from 1 to 2. So let me go ahead and get myself placed on the x-axis where x is 1 and x is 2. So these lower and upper limits here, these values are our x and y values. So starting at x equals 1 and concluding at x equals 2, let's go to x equals 1. Let's find the curve. Here it is. Think of that as being your vertical barrier. Okay, now I'm going to collect the space from the curve to the x-axis from x equals 1 to x equals 2. Got it. I want to find the value of this region in here. And we have a geometric shape of a trapezoid, so it'll be as easy as finding the area in a or using the trapezoid formula for area, and we'll have the value of the integral, because that's what this represents, a collection of area from this beginning x to that ending x, from the curve of f prime of x, whatever it is, to the x-axis. And because I'm comparing the x-axis to a curve that's above the x-axis, we're going to say that the value is going to be positive. Okay, so for me on this one, let me calculate the area. So this is going to be exactly, it's not going to be an approximate because this geometric shape is exactly a trapezoid. So the height is 1. Sum of the bases. Right, base 1, base 2. Well, for me to find the value of this base right here, I need to know its vertical distance. Well, I know this is 0, y equals 0. What is this y value? I can subtract those two y values and get the height, which is simply going to be the functional value. So if I plug in 1 for x, then I know this point is 1, 2 on f prime of x. So the base is 2 here. Plus, plug in 2 here, evaluate the function. This ordered pair is going to be 2, 4. So this base is 4. Sum, divide, I get 3. All right. So the value of the integral is 3. Moving on to number 2. Take a look at number 2 now. We are going to actually accumulate the value of the integral from 0 to 3. These are our x values under the same curve. So here's 0, and here's 3. So in a different color, I know it's going to get kind of crowded, but in a different color, hopefully that'll help us visualize what's going on. So at 3, I'm going to go up to the curve, and it might kind of go off my screen. But if I think about it, if I plug 3 into the function, the derivative, I'm going to get the ordered pair 3, 6 here. So this y coordinate of that intersection is 6. And then, of course, this point right here, if x is 0, is going to be 0, 0. All right, so if I kind of looked at that geometric shape, I can see that it's a triangle. So at this point, I'm going to come down here and find the area in that triangle. So I'm going to actually just say it's equal, not approximate. The base of the triangle is going to be 3. The height of the triangle is 6, so base times height divided by 2. It appears that the value of my integral from 0 to 3 is 9. And I don't know if you've been looking back over here and making connections to these values and these values here, but if not, this might be a good time to do so. Let's find number 3's answer. All right, so in a different color, let's look at the integral from -2 to 2. So where x is -2, over here, come down to the curve, perhaps right here. This is -2, -4. I want to collect area, if you will, or the space between the curve and the x-axis for x values between -2 and 2. Well, if I'm over here from 0 to -2, the curve falls below the x-axis. So in that case, I'm talking about finding this value right here. If I'm 0 to 2, then I'm talking about finding the value of the integral from here. Well, these are both triangles. We're going to find the area in both of these, but if I'm comparing this curve with the x-axis, part of the curve's below, part of the curve's above the x-axis. So in fact, these two values will undo each other. This will be our negative value and this will be our positive value. All right, so coming down here, if I had a representation of both of these values here, I mean, if you wanted to think about it, you could actually split up the integral into two integrals using a property. You could say that this is the integral from -2 to 0 of f prime of x plus the value of the integral from 0 to 2 of f prime of x dx. So using a property to split it apart here. Okay, and then for this integral right here, if we're collecting the space between -2 and 0, I know that it's going to be the opposite because of the location with the x-axis and the curve. And let's find the area. So the base is what? 2, the height is 4, divided by 2. Plus, over here for this triangle, all right, so hopefully we're seeing the connection between the value of the integrals and the change in the y values on the regular graph. So let's take away from this experience right here and why these are equal, because they're not, it's not by coincidence, that when you integrate a rate, this being a rate, this integrand being a rate, a derivative, when you integrate a rate, you get back to the original function f. Okay, you're finding the change in the y-coordinates on the regular graph at the corresponding x's. So if you can kind of pay attention here, these two x's, 1 and 2, are my input values here. These two x's here, 0 and 3, are my input values here, my x's here. So integrate a rate, you get back to the change in the y-coordinates on the regular graph. And why do we care? Well, sometimes we have information about a rate. We can collect data about a rate. Okay, and then if we can collect data about a rate, it gives us some idea of how the quantity is changing over that specific x interval. So that's the connection that we should take away from here, is that the answer to the integral is actually the change in the y values at those corresponding x's on the antiderivative. So previously you were finding antiderivatives. We're going to need to do that for our next lesson. Previously you were approximating the value of an integral using area formulas. And so that was the connection here, and why I wanted you to do that, so that you can kind of eventually get to these numbers to make this bigger connection. Okay, so down here in this space provided down here, I'm going to rewrite the connections that occurred right here. Okay, so if I said consider the integral from 1 to 2 of f prime of x dx, that is, I said consider this. If I knew what that answer was, it's going to be equal to the regular function f, the antiderivative, if you will, evaluated at 2, minus the antiderivative f, evaluated at 1. All right, let's make another connection. The second problem. The value of the integral from 0 to 3, 9, is equal to the change in the two y-coordinates at the corresponding x's, f of 3 minus f of 0. I'm building. Looking at the third example, it's going to be equal to, just want you to notice the structure. Look what I'm writing here. I'm not writing f prime. I'm writing the notation that represents the antiderivative for f prime. So it's f evaluated at the upper limit 2 minus the antiderivative evaluated at the lower limit, -2. Okay, and without reversing these limits, that's okay. Just know that the proper algorithm says, okay, if I have this, no matter the placement of the limits, I know it's the antiderivative at the upper limit minus the antiderivative evaluated at the lower limit. And it'll all take care of itself, and we'll get the sign that we need. But that's the actual correct way to, in the order, to put that together. right, now based on these specific examples right here, what I want to do is I want to kind of generalize. So I'm still working down here. I'm going, okay, well, let's go to a generic formula. And that generic formula is going to be our fundamental theorem of calculus. This is the connection between a function, its derivative, area, values of integrals, etc. Okay, I'm going to a general integral. Lower limit's going to be a, upper limit's b. Don't know what those numbers are? Doesn't matter. They're both x values. F prime of x dx. Okay, what would that equal? Well, if somehow I could integrate f prime and get back to the original function, I could say it's the functional value at b minus the functional value at a. There are many versions of the FTC. This is the FTC, the Fundamental Theorem of Calculus. There's many versions, so I just want to take a look at something right now too that's a little different. What if I had the integral from a to b and I didn't use the prime notation? I just used f of x. Okay, well, just using notation, I could say, well, all right, well, what's the antiderivative for f? Well, I can't go back to f because it has to be different. Well, maybe f is the derivative of uppercase f. That's common practice. So that just means the value of this integral from the function to the x-axis on those two x's would be the difference of the y values, f of b, capital F of b, minus capital F of a. All right, so I'm going to come up here. We're going to continue with notation. Okay, let's say we had the integral from a to b of acceleration as a function of time. All right, well, let's think about integrating that rate. Well, acceleration is the derivative of velocity, so we're going to go back to a velocity symbol evaluated at the upper limit minus velocity at the lower limit. So if I could find the value of this integral, it tells me the change in the velocity, in whatever units I might be working with from a to b. Okay, what about this? If I integrate this rate equation, velocity, I'm going back to position. PVA. I'm going from A back to V up here, and then from V back to P. Well, if I integrate the velocity, it's going to give me the change in the position of the object. Well, perhaps my object is moving horizontally. If my object's moving horizontally, then we usually let the letter x represent its position. So I'd say x, the antiderivative, evaluated at b minus x of a. So this is really kind of reserved for horizontal motion. Let me just go ahead and look at an alternate form. If we're talking about an object moving vertically up and down, straight up and down on some vertical line, the antiderivative for that would probably be the letter y. You will know in context if they want you to use x or y for the position function. So I'd say the antiderivative of velocity, if my object's moving vertically, is y, so it's y of b minus y of a. Okay, so the change in its y, its movement on that time interval. All right, so for this particular worksheet, I just wanted you to see the connection between the change in y values on a function and that answer that you get, and its connection to the value of the integral from the curve to the x-axis when you're talking about finding area. Okay, so a big connection there. The fundamental theorem of calculus results. And down here, just wanted to show you the different forms that you might see the FTC in. Okay.